So let's continue talking about derivatives. And let's say that maybe we wanted to look at the function f of x equals x squared. And let's say I wanted to know what the derivative was at, well, let's say maybe at 1. So that means then in our notation, I'd be finding f prime of 1. But maybe that's not the only thing I wanted to know. Maybe I also want to know what f prime of 2 is, and f prime of 3, and f prime of 4.7. Okay, so let's just say that I wanted to know lots of different slopes of tangent lines for this particular function x squared. Let's just go ahead and draw it. Okay, so there's our function x squared. So again, maybe I want to know the slope of the tangent line at numerous points and not just at one particular point. So of course I could start off with our definition of the derivative. So derivative at a point A. Generally, this is one of our definitions. The limit as h goes to 0, f of a plus h minus f of a all over h. Now remember that lowercase h was the distance between the 2 points that we attached our secant line through, and we wanted that secant line to become a tangent line, so we want the distance between the 2 points to be going to 0. H should be going to 0. Okay, now I could do this 4 times for the particular a value, 1, 2, 3, and 4.7. That might get a little tedious though, because we know from experience that these tend to take a little bit of time. So let's see if maybe we can come up with a better way of finding these derivatives. So instead of doing it numerous times and plugging in specific points for a, what if we were to keep a as a variable, and then when we're done evaluating the limit, we could just plug in the numbers when we're done. Okay, so and actually instead of making it an a, I'm going to go ahead and I want to go ahead and say it's x, because really we want to go ahead and do this for a variable. This is more, the slope of the tangent line at a particular point. This we could think of as the slope of the tangent line at any point, just whatever x value I happen to want to plug in. So if I replace a with x here, oops, h goes to 0, I'd have f of x plus h minus f of x all over h. And what I should get out of here when I'm done is another function. So I'm starting out with the function x squared, and after I'm done with this, I'm going to get out another function that essentially will tell me the slope of the tangent line at any point. Okay? Let's go ahead and go through the work and do that. So I'm looking for f prime of x. Again, I have the limit as h goes to 0. Now let's go ahead and plug in some values here. So my f function in this particular case is x squared. So if I look at f of x plus h, my f function is saying take whatever I put in, which is x plus h, and square it. That's my function. And then of course f of x would just be x squared all over h. Okay, so this should look kind of familiar. Notice if we were to let h go to 0 right now, I'd have x squared minus x squared, which would be 0, divided by 0. So that's indeterminate form. So we're going to use algebra to simplify this. Simplify it so that it becomes continuous at 0, and we can just go ahead and plug in 0 for h. So let's go ahead and distribute this x plus h squared. Okay, so we get x squared plus 2xh plus h squared. Okay, now if you don't quite remember how to do that, we're just looking at x plus h squared, which would be x plus h times x plus h. There's my x squared. I'd have 1xh, 2xh's, and then an hh, so h squared, minus our x squared all over h. Now one thing I'm noticing that can simplify here is I have an x squared minus an x squared. So I have the limit as h goes to 0 of 2xh plus h squared all over h. It's looking better than when we started, but I still, if I let h go to 0, I'll still have 0 over 0. But I do see here that there's an h in each term on top. So let's go ahead and pull that h out. If I pull an h out, I'm left with 2x plus h. Okay, and the reason I wanted to do that is because the h's now cancel, and I get the limit as h goes to 0 of 2x plus h. Now, we're going to let h go to 0, right? Notice this is continuous at h equals 0, unlike all of the other ones that we had before. So that means I can just plug in 0 for h, and I get 2x. Now let's think about what that means. So that means that I took the derivative, I didn't plug in a specific number, I just kept it as an x, and I see that I get the function 2x as my output. So what that means is, and I'd like you to notice a few things here. If I plug in 0, notice I get 2 times 0, which is 0. And let's not forget that this means the derivative, the slope of the tangent line, at whatever the input is. So in this case, at some value for x, essentially whatever we happen to plug in. So if I plug in 0, this is the slope of the tangent line at 0. And just go ahead and think about that for a second. Does that look right? Should the slope of the tangent line at 0 be 0? Well, let's look here. There's the point 0, and sure enough, I see kind of a minimum point there. And if I draw a tangent line, I do get a slope of 0. All right, if I plug 1 in, so these were some of the values I was interested actually. 2 times 1 is 2. Okay, so that is the slope of the tangent line at x equals 1. Sorry, not 2, at 1. So if I pick the point 1, maybe right here, that means that the slope of the tangent line at that point is 2. If I were to plug in maybe the next number, like 2, I'd get 2 times 2, which is 4. So that would be telling me then the slope of the tangent line at x equals 2. Notice that this function actually tells me quite a bit about this function, because it's saying that for every x value I go further, I kind of missed my curve here, for every x value I go over, my slope increases by a factor of 2. That is, this slope is 0, this slope is 2, this slope is 4, and if I go over to 3, I'll double my slope, I'll get 6, etc. And another thing I'd like you to notice is that if I were to put negative numbers into the derivative, I get a negative out, right? For example, if I plugged in -1, I would get -2. And notice that that is the slope of the tangent line here. Same as this slope, but a negative slope. So if I plug in a negative, I get a negative. And as you see, if you put a point anywhere along here, you're going to get a negative slope. Over here, positive, right here, 0. Okay, so that's one of the great things about looking at a derivative, not necessarily at a point, but as a function in itself, because one, it makes it a lot easier to find the slopes of the tangent lines, or the instantaneous rates of change, and two, the derivative actually tells you quite a bit about the original function, kind of how it's behaving. Okay, so let's go one step further here. Okay, so we looked at x squared. Let's maybe take a look at x cubed instead. And now, again, let's say I wanted to know the derivative at a bunch of different points. So what we're going to do is we're just going to find the derivative at x. So we're going to do a similar process to what we had before. I'll have the limit as h goes to 0, f of x plus h minus f of x all over h. And let's go ahead and do this for x cubed. So what I would have is, again, my input is x plus h. My function says cube whatever the input is. So I'd have x plus h cubed minus, the function is x cubed, all over h. Now again, notice that if we let h go to 0 now, I'm going to get 0 over 0. That will always be the case because if h equals 0, that means we're trying to find the slope between 1 point. We need 2 points for that. So that's why we're approaching 0 here. So that means that we need to rewrite this so that it's continuous at 0, and then we can go ahead and plug it in, just like we did with the other one. So that means that what we want to do is we want to rewrite x plus h cubed, which of course means it's x plus h times x plus h times x plus h. Okay, so the easiest way to do this is to think about separating it into different pieces. So we'll look at that first two first. We actually did that work already. It was x squared 2xh, h squared. And then now we'll distribute, just make sure each piece goes to each piece. So that would be x cubed, then I'd have an x squared h, then I'd have a 2xx, so x squared h, Now to this one, 2xh squared. And we're almost done. H squared x, h squared h, so h cubed. Okay? So let's see if we can combine any like terms here. I see there's only one x cubed. I have an x squared h and 2x squared h. So that'd be 3x squared h. Similar, here I have 2x h squared and an h squared x, which is the same as an x h squared. So I have 3 of those, and only 1 of the h cubed. Now here's one way I'd like you to think about this. It wasn't too hard to distribute all this, but maybe I wanted to go to a 4th or to a 5th, and maybe we should see if there's a better way of thinking about how we can expand something like this. So one thing I'd like you to notice is, actually let's jump back to the x plus h squared for a second. So from here to here. So notice when I have an x plus h squared, the only possibilities I could have is an x squared, that is by multiplying an x and an x, an h squared by multiplying an h and an h, and then an xh by multiplying the x and the h. That is when I go and I distribute everything. So notice that I have 2 xh's because there are 2 ways I could have gotten an xh. I could get one as an xh or an hx. And that's essentially, this is my xh, this is my hx. Those were my 2 possibilities of getting that. Okay, let's just look back real quick at x cubed. So what I mean by that is I'm going to have an x cubed. I'm going to have an x squared h, because that would be done by taking an x, and an h, or maybe some other ways. I could have an xh squared, and I could have an h cubed. And let's think of all the different ways we could get those, and that'll be our coefficients. So there's only one way I could get an x cubed. That's an x times an x times an x. There's no other way. So there's a 1 in front of this one. An x squared h, well, let's see, I could have an xh. Okay, so that would be like taking this x times this h. I could also have an xhx. That would be like taking this x times this h times this x. And I could also have an hxx. That looks like the only 3 possibilities there. So my coefficient is a 3. 3 different ways of making an x squared h. Here, this is going to be really similar. I could have an xhh, an hxh, or an hhx. 3 different ways. And then, of course, the only way I could make an h cubed is to have 3 h's being multiplied. So there's a 1 here. 1, 1. Okay, hopefully that makes sense. Maybe we're going to do it for the 4th also, so it might make more sense with another example. So that means that what I have here is this part simplified, which is this, x cubed, 3x squared h, 3xh squared, h cubed, minus the x cubed, all over h. Okay, let's see if we have some cancellations. I'm seeing an x cubed and an x cubed. And I'm going to go ahead and skip a little step here for a second. Let's go ahead, now that we canceled these, let's go ahead and imagine that they're gone. And now I'm also seeing that there's an h in each of the terms that are left in the numerator, each of the ones up here. So let's go ahead and factor that h out right now. If I do that, I'm going to be left with a 3x squared and a 3xh, right, I'm pulling one h out, and an h squared. And I'm still dividing by h. Those will cancel. I'm going to go ahead and just skip another little step here. Let's cover this up. You might not want to skip these in your notes, though. You might want to write all these out. So if I cover these up, those are gone. So now I want to do the limit as h goes to 0. And notice this is now continuous. So as h goes to 0, this piece goes to 0. That piece goes to 0, which means I'm left with 3x squared. Okay? So that means that the slope of the tangent line for x cubed is 3x squared. So if I wanted the slope of the tangent line at 1, I plug in 1. Slope of the tangent line at 7, plug in 7. Okay? So it makes it very nice if you want to look at the slope at many different values. Here's another thing I'd just like you to notice real quick about this one. Let's think about the function x cubed. Looks kind of like that. Okay? Notice if I were to draw a tangent line anywhere, let's just pick a point here, notice there's positive slope there. Positive slope, positive slope, positive slope. So do you see how with the tangent line along x cubed, it is always positive, except right here where it's 0. So do you see that? It's always positive. Notice my function. My function is always positive. That is the derivative. The derivative as a function is always positive. And that's because the slope of the tangent lines for x cubed are always positive, except for at 0. Notice if we plug in 0, we do get 0, just like we see graphically. Okay? So again, the derivative also tells us a lot about the function and how it's behaving. Let's go ahead and take this one step further here, and then I'm thinking we can probably start to see a pattern. So let's look at x to the 4th, and we're going to find the derivative. So let's go ahead and set it up again. Derivative. I think you're going to like what's coming next, because we're going to find a rule pretty soon here that makes us not have to do this every time for these particular functions. Okay, but we got to work our way up to it a little bit. Okay, so that means we are now looking at x plus h to the 4th minus x to the 4th all over h. So now we need to look at how do we expand x plus h to the 4th. So using that same idea, we know that we can create an x to the 4th. That would be taking an x times x times x times x. I could also have an x cubed h. We're going to think about what this coefficient should be. I could have an x squared h squared. I could have an x h cubed. And I could have an h to the 4th. So you see, those are the only possibilities that I have. An x squared h and an x squared h squared and an h squared x squared are equivalent to each other. So that's why we don't have two different possibilities here. So those are all the different ways that I could, or the different kinds of combinations that I could have. Okay, notice x to the 4th. The only way I could make that is 4 x's. So we have a coefficient of 1. An x cubed h, I could have an xxxh, xxhx, xhxx, hxxx. Okay, so those are all the 4, so we have 4 different possibilities for making an x cubed h. Now an x squared h squared, let's see how many we could make with this. This, of course, is a possibility, xxhh. You know, there's really no right way of doing this. Let's just see if we can think of all the different ways. Maybe xhxh, hxhx, hxxh. We could go the other way with that one, xhhx. And I think there's one more here that we could do. Yeah, kind of like this one, hhxx, just flipped. I'm pretty sure, yep, that's all the different combinations that we can make. This is probability, by the way. We're just looking at all the ways that we can make combinations of x's and h's. So let's look again at xh cubed. Now notice that's really no different than x cubed h. So we're going to have 4 possible ways of doing that. Basically the same as these ones, except switch the x's and h's. This one, of course, we only have one way of doing that, all h's. Okay, so let's look at that then and see if we can do some simplifying. So I'd have x to the 4th, 4x cubed h, 6x squared h squared, 4xh cubed, h to the 4th, and then of course my minus x to the 4th, all over h. Okay, I know this is getting a little tedious, but we'll start to see some things happening. X to the 4th cancel. Again, I'm going to kind of skip a teeny bit here. I see again there's an h in every term. So let's look at the limit as h goes to 0. Pull an h out. Okay, again these are canceling. And now let's look here. There's an h in all of these terms, but not this one. So that means that if we let h go to 0 now, after these are being canceled, all of those are going to go to 0, but this one will be remaining, and I'm left with 4x cubed. All right, let's just do a little quick recap here. So here was my function. Let's do a table. Here was the derivative. So if you want to look back at your notes here, we looked at x squared, and the derivative was 2x. We looked at x cubed. The derivative was 3x squared. We looked at x to the fourth, and we just saw it was 4x cubed. So I want you to just think real quick, if we did x to the fifth, I know we're not going to go through and do all that work again. If we did x to the fifth, just think about what you think the derivative would be. Let's see. It looks like it would be 5x to the fourth, doesn't it? Essentially we're bringing that 4 down in front, or the number, the exponent, down in front, and then we're taking 1 away every time. This is like 2x to the first. So we're bringing the exponent down in front and then taking 1 away. This is what we call the power rule, and this is going to be one of our absolute favorite rules that we learn. So the power rule means for a function like a power function, that would be x to the n. The power rule says that if we look at the derivative, it is n times x to the n minus 1. Okay? That is, we take the exponent down in front, and then we take a power away. So there's the power rule. So now that we know that, we can start using this instead of having to do, use this limit definition every time. And this works for any number here. It doesn't have to be a whole number. So if I wanted the square root of x, where n would be a half, I could start using this. And then we don't have to use the conjugate. Okay, so now that we have the power rule, I'd like to talk about some other notation as well. That is, other notations for the derivative. Now, we've already talked about what we call prime notation. So prime notation is, if I have my function f of x, then the derivative is f prime of x, written like that. That could be the same thing for y. Sometimes we don't call it f of x, maybe it's just y equals, and then the equation. And again, if I want to look at the derivative, I could also say just y prime. So this, we've had some familiarity with this notation so far. Here's another notation that we haven't worked with just yet. What it's called is Leibniz notation, and that's a pretty famous mathematician, one of the inventors of calculus. Newton was the other. And he kind of had some different notation. Newton preferred this one. Leibniz had his own notation that he liked. And we're going to use them interchangeably because sometimes one works better than another in particular situations. So the Leibniz notation is written like this, dy over dx. Okay, and so what Leibniz notation is meaning, this might look kind of familiar. If you think about, instead of a d, like a delta, change in y over change in x, that's pretty much exactly how we calculate the slope. So this is kind of an intuitive way of writing it because it's essentially what it is. It's the slope, the change in y over the change in x. Another way that we could write that is df over dx. We don't use this one quite as much. We usually use y when we do Leibniz, but you can use this one too. This says the exact same thing as f prime of x. And this says the exact same thing. Let me write that. This is the same thing as y prime, essentially. And this is the same thing as f prime of x, essentially. Okay, so we'll use those interchangeably. Let's just look at an example really quick, because I would like us to get a little bit more comfortable with this new notation. So examples of the various notations. Let's say we had the function f of x equals x to the 7th, or y equals x to the 7th. So if I used prime notation, I could say then that f prime of x equals 7x to the 6th, right? Power rule. I just used the power rule there. Bring the 7 down, take 1 away. 7x to the 6th. So that's our prime notation. And the same thing here, I'd have y prime equals 7x to the 6th. Okay, exact same answer, just a different way of writing it. Now let's look at Leibniz. So the way Leibniz would write this is he would say df over dx equals 7x to the 6th. Or written this way, he would say dy over dx, that's a y, kind of look like a g, equals 7x to the 6th. Okay, so prime notation, we're kind of used to that one. Leibniz notation. Let's try to use both of them as often as we can just so we get comfortable with the two. Okay, here's another way of writing it, because we don't have enough notation already, huh? Another way of writing it, and you'll see why this is a good way of doing it, is if I wanted to know the derivative of x to the 7th, another thing I can do is just write out in front of it, write d over dx. Okay, so this is saying what is the derivative of the thing in front of it, x to the 7th. So in this case, I would write 7x to the 6th. Now, the reason why this is good notation, you're going to see this notation a lot, is because I don't have to say what the function is and then ask you for f prime. This right away tells you what the function is and then take the derivative of it. So this is a very nice condensed notation, and so that makes us happy. We like condensed notation. So you'll be seeing this one quite often. Now, one thing I see a lot about the confusion between this new notation is the difference between dy dx and d dx. Okay, so let me just tell you real quick what those differences are. dy over dx, I want you to think of this as like a noun. That is, it's a thing. This would be like a number or a function. It is the derivative of y with respect to x. This one, this is more of like a verb or an action word, because this is like an operation. This is saying what is the derivative. It's saying what is the derivative of whatever's in front. So that means that this can stand alone by itself. This means the derivative of y with respect to x. This needs something to go along with it, because this is a verb, it's an operation. It's saying do something to whatever's in front of it. So you'll never see this piece alone, you'll always see it with something in front of it, like this. And it means to take the derivative of that thing, okay? Once you see a little bit more, you'll get a little more comfortable with it. All right, let's just do a few more rules here that will help us in differentiating. Power rule is going to be one that you are going to be using a lot. One of them is the sum and difference rule. Okay, so that is if I have two functions being added or maybe subtracted from each other, and if I want to look at the derivative of that. And so you might actually be able to guess this one, but if I have an addition or subtraction, I can essentially just take the derivative of the first thing and then add or subtract, depending on the operation, the derivative of the second thing. Okay, so there's another rule. And again, just for the sake of getting comfortable with these notations, I could also write this as f prime of x. And I could write this as g prime of x, or df over dx. I could write it that way also. Okay, another one is the constant multiple rule. Okay, and that involves when I have a constant times a function, so this is some number, and I take the derivative of that. What I can do is I can essentially just bring that constant out in front. I can take the derivative and then just multiply by c when I'm done. Okay, and then again, just for notation purposes, that's another way I could write that. Okay, let's just look at two more rules here. One of them is if I have the derivative of a constant. Let's think about that. So a way I could write that is the derivative of some constant. Let's think about what that would be. If you think about it graphically, I think about graphing a constant, something like y equals c. Well, depending on the value of c, it may be above or below the x-axis, but either way, it's going to be a horizontal line. And so when I take the derivative, again, that's saying the slope of the tangent line at any particular point. Well, notice any point I pick along here, if I draw a tangent line, I get the slope of 0. So the derivative of a constant is 0. And last but not least, if I look at the derivative of a line, okay, one way we could write that is the derivative of, and I'd like to be as general as possible here, so general equation of a line mx plus b. And if I think about graphing a line, of course it's linear. Of course these are both lines, but the difference is this one actually has some sort of slope to it. If I pick any point along here and draw the tangent line, think about what the slope of that tangent line is. Well, of course the tangent line is the same as the line itself. So the slope of the tangent line is the exact same as just whatever the slope of the line is to begin with. Now the slope of the line is m, based on our equation. So the derivative of a line is just the same as whatever the slope of the line is. Okay, so all of these combined will start to make taking derivatives a lot easier. And as we go through the class, we're going to learn more and more rules for finding the derivatives as functions.